So welcome everyone to the first session in the ZP&C stream. This session is 5A for your feedback. Sorry, I'm still admitting people. It is acting on near real-time SMF data and will be presented by Stephen Thomas and Frank Tiedemann of SMT Data. As I just mentioned, and as if you joined the conference opening, the feedback is really important to us and to the speakers. So please do that. Any questions, please put into the chat. So we are still admitting people, and I will continue to do that, but I will hand over now and say thank you to Stephen and Frank.
Yeah, thank you very much, Angie.
Thank you.
So we can just start out a little bit slowly while people are still joining. And just again, what we're presenting is acting on near real-time SMF data. So it's about sort of proactive mainframe performance and capacity and cost management. And what we're going to be going through is a little bit of the background. Why is it interesting to look at near real-time SMF data, and what do we actually mean by near real-time, and then talk about some of the use cases. Where could it be interesting to be doing this kind of analysis where we're proactively looking at the SMF data, rather than just doing historical analysis of yesterday's or last week's data. Dig into some of the specific SMF data types that are interesting for these use cases. And then we'll dig into some examples. We'll have one example we're going to go into in a lot of detail, where we're looking at different ways of approaching it. And then we'll take some other examples at sort of a more high level to discuss them. And then finally wrap up with, well, what are some of the challenges when you're dealing with near real-time data, and some suggestions for dealing with those. As mentioned, please feel free to put questions in the chat along the way. We will have some time at the end for question and answers. We would really like also some feedback on this. This is the first time we've been presenting this particular topic of looking at SMF data in near real time, and particularly use cases. We're really interested in getting a dialogue going about, what use cases, in addition to the ones that we're presenting, could be useful to dig into. Good. So maybe just a couple of words before we start in the presentation about who we are. I'm Stephen Thomas. I've been with SMT Data for about 14 years now. My title is Principal ITPI Evangelist, which means I do stuff like this, community profiling the product, but also customer onboarding, and very much involved in customer projects, particularly around analyzing SMF data. Frank, you want to say a couple words about yourself?
Yeah, my name is Frank Tiedemann, and I've been system programmer, mainframe architect for, I think, 35 plus years, working with capacity and performance, of course. I think the first mainframe I sized was a CMOS generation 2 back in the 90s. I joined SMT Data 3-4 months ago. And of course, been working with these guys for a long time. So that's my background.
So just a couple words about SMT Data. And again, this isn't a product presentation or a company presentation, but just to know who we are. SMT Data is a software and services company based in Denmark. And we focus primarily on mainframe capacity and performance. So this is about processing particularly SMF data and providing tools and consulting on top of that to help people with mainframe capacity, performance, and cost analysis. We have a lot of the larger mainframe installations in Europe, and some in North America also as our customers. Good. So when we talk about near real-time analysis, what do we mean? Traditionally, when you look at SMF data, a lot of the work is focused on historical capacity and performance data. So you're looking at yesterday's data, you're looking at trends over the last few weeks or the last few months. You use it to predict how much capacity we're going to need next month. When should we upgrade? Should we change our LPAR configuration? What are our top consumers that we should be out optimizing? But a lot of the historical analysis is really, about getting lessons learned and planning for the future. But sometimes you want to react in much shorter time, so you want to be able to see what's going on in the system right now and react before things get out of hand. So for the purpose of this presentation, when we talk about near real-time analysis, we're talking about something where you can go in and understand the situation early enough to be able to act on it before it becomes a problem. So in the context of mainframe performance and capacity, this means being able to do something within sort of 10 to 30 minutes, 10 minutes being sort of the shortest amount of time a human can look at some data, analyze it, understand it, choose an action and execute that action, and 30 minutes being so far in the future that it's not really real time anymore, that you really don't know where the system's going to go. So we're focusing kind of on that window between 10 to 30 minutes in this presentation. So let's take some use cases where it's interesting to do this kind of proactive analysis. One of the classic ones is looking at the 4-hour rolling average MSU, because if that's leading up to a capping situation or just a new monthly peak, and if you're paying for your capacity based on the rolling 4-hour average, which many customers still are, even though some have moved over to tailor fit pricing, this is still a very relevant use case for some people. Even the ones who've moved to tailor fit pricing, often they still have third-party software being billed based on the rolling 4-hour average. But also a lot of customers still have some soft capping in place, and capping is not a good thing to run into. Even though Workload Manager is hopefully going to handle it well if that's well set up, there are going to be a lot of disadvantages to running into a capping situation. So, and we'll spend a lot of time on this particular use case discussing how can we detect that we're heading towards a new peak or crossing some threshold in our rolling 4-hour average MSU usage. Some other cases that can be interesting to look at is zip eligible workload running on CP. It's much cheaper running on the zip. You don't generally pay for software running on zip. But if you're running out of zip capacity, then the system will typically spill it over and run it on the CP, which is both going to have some cost and potentially some capacity and performance implications of doing that. So being able to catch that in near real time and react to that is important. Similarly, when we look at vertical affinity, now the mainframe will assign CPUs to your LPAR based on low, medium, or high vertical affinity. High vertical affinity, you're more likely to find your data in cache. Things will run more effectively. So if you see a decrease in vertical affinity, that might be something you want to react to, because that's going to, again, affect cost and performance. Looking at some of the other records against some of the subsystems, CICS response time, a sudden jump in the CICS response time is something you might want to react to, because that's going to be affecting your users. Number of CICS abends, a sudden spike in abends is something you probably also want to react to in close to real time. Transaction looping, similarly. Other subsystems, a typical one we see a lot is DDF workloads. Something is going on out there on a server, getting or writing data to DB2, and suddenly you're seeing spikes there, and you want to be able to go in and deal with that in near real time and not just look at it the day after. Looking at the available capacity as a percentage of the available looking at the high importance workloads as a percentage of the available capacity is also important. Workload manager statistics, things like performance index can be also an important one to look at in near real time. In the end, all of these cases are about cost. We're heading into something that's going to cost us a lot of money, or performance. We're heading into something that's going to give us poor performance on our high importance workloads. Good. So these are some of the things we're going to talk about. We'll focus very much on the first one to go on to a lot of depth and talk at a high level about the other ones. But as I mentioned at the beginning, we're really interested in hearing from you about what other use cases you see for doing this kind of analysis. Good. So some examples of the relevant SMF data that we could look at, SMF 70, if we're looking at the KEX, Sysplex, LPAR level, we'll be looking a lot at SMF 70 in connection with this rolling 4-hour average MSU discussion. SMF 72 to look at workloads, but also to look at what's going on in Workload Manager. SMF 30 to look at address spaces or jobs. And then the subsystems, SMF 101 to look at DB2 and particularly DDF, and KICS with the SMF 110. And there's obviously a lot more records we could be looking at, but these are the ones we're going to be focusing on. And yes, we'll come back to it at the end, some of the challenges in making this happening. SMF 70 is a very small record, and reading that one in close to real time and analyzing it is going to be a lot easier than something like the SMF 101s or 110s, which may be 100 times bigger, 1,000 times bigger than the SMF 70 records. So, good. So if we look specifically at the SMF 70 and specifically at this use case where we want to try and predict where the 4-hour rolling average MSU is going, a couple fields that are interesting is the SMF 70 LAC, which is the long-term average CPU service in MSUs at the end of the interval. So this is the one that's used in the SART, for example, to calculate the 4-hour rolling average MSU for billing purposes. So this one is quite important. But it is a rolling average, and it doesn't give you a really clear picture of what's going on right now. So we also like to use the SMF 70 EDT, which is the effective dispatch time in seconds, CPU seconds. And in order to convert that to something we can compare with the LAC, we can use the SMF 70 CPA actual and scaling factor to convert from seconds into MSU. And that'll give us the amount of MSU used in the interval. And of course, then we can calculate that in terms of what it's using per hour to compare it with the LAC. But we'll show you some of those calculations in a minute. Good, so just putting those two numbers into a graph, and we're just showing 24 hours here in 5-minute intervals. Now, different installations run with different RMF intervals. In this particular case, we're looking at 5-minute intervals. And this is an interesting topic when you're looking at near real-time data, because if your RMF interval is 15 minutes, then it's going to be a little bit longer before you can see these numbers. So, this could be an argument for running with shorter RMF intervals if you want to do this kind of analysis. In this particular case, and all the examples we'll be showing will be with 5-minute intervals. So the blue line is the rolling 4-hour average, and the green line is based on the effective dispatch time converted to MSU hours. So the real question is, as we move here through the day, we can see we have a little bit of a peak in the middle of the day, but our real peak is going to be in the evening here. And so the question is, can we, in the hours up to this peak, have some indication that we're heading towards the peak so that we can react potentially by capping or doing something else to to avoid this cost. And Frank will discuss some of the actions you can take when you discover you're heading towards that. So the example we're going to go through, we're just going to look at this period right up to the peak. You know, as I said, real-time analysis, near real-time analysis, we're looking at something we can do in sort of a 10 to 30-minute time frame. So we'll look at it about a 45-minute time frame here in the example that's coming. So with that, I'm going to hand it over to Frank to go through the specific example.
Yeah, so let's zoom into the 4 hour up to the peak. As you see here, we have set a threshold of 3,150 MSU. That's where we want to know that we don't want to cross it. It could be due to software cost, due to the entitlements we have for our software. It could be due to where we have set our capping. We don't want maybe to go into the capping situation, or it could be just performance, because we know when we hit this limit, then our response time starts to be slow. And we're still on the 5-minute intervals, and the blue line is the LAC, so that's where you can see that the MSUs are not now climbing towards the threshold. The thing here that we want to predict is, are we going to break the threshold? Are we going to hit the threshold, or will we stay within the threshold so we don't need to worry at all? And of course, we need to have a time period before this actually hits the threshold, so we can take action. So next slide, please. This is a first method, simple projection based on the LAC. The LAC is already an average, so starting to make more averages out of that is probably not so good. But in this case, the difference between now and 5 minutes ago is calculated as 32 MSUs, and then you do a projection that will give us approximately 5 intervals until we hit the threshold. If we keep doing the same work or using the same amount of CPU as we have done for the last 5 minutes. The calculation is the difference between our threshold and where we are right now, and divided by that 32 MSU, which is the climb for 5 minutes. So that will give us 4.9 intervals until we hit the threshold. Next slide, please. Then we can decide to look at the SMF 70 EDT, the effective dispatch time as well. So that's in the blue line is still the LAC, so that's where the MSUs are now, and then we have a current usage on the system which is actually above the threshold. We haven't broken it in our 4-hour rolling, but since it's above, there is a chance that we will do it. Next, please. So the calculation is a bit different here, because then we take the difference between the current use and the 4-hour rolling, and calculate that on an hourly basis, since it's MSU hours. So the expected climb in the 4-hour rolling average is now 22 MSUs. This will give us a little bit more time to react, since it's 7.3 intervals out in the future before we hit the threshold. Yes. However, if the workload suddenly goes down, then the projection will be, less likely to go over the threshold. So if you have an interval where it goes down, you will see, like here, 5 minutes later, that the the CPU usage has fallen, and now there's no chance that we will go over as this projection calculates.
Yeah, and so really what this is showing is that while using the SMF 70 EDT, the effective dispatch time, is going to be much more sensitive because you're not dealing with rolling 4-hour average. It's also going to be much more volatile, that, you know, it's going to change basically from interval to interval what you're predicting, whereas the other approach was much more stable but less sensitive.
Yes, please. So what actually happened? The reality, the 4-hour rolling average crossed the threshold at the 6th interval, which is between 5 and 7, which we calculated in our projections. The projection was done at interval 2 here. And it gave us 5 interval on the light green line, and it gave us 7 interval on the pink line. The dark blue line crossed around interval 6, right? For the pink one, the projection 5 minutes later, which is in interval 3, showed that we would flat out just because the utilization fell below the line. So using either of these as projection is probably not the best way to go. Yes, please slide. So what we need to take into account is that the 4-hour rolling average is actually a sliding window, meaning that when you get your next 5-minute measurement, the oldest 5-minute measurement will disappear. It's basically 48 measurements that are averaged out and ends up in the SMF 70 LAC. So next one. So now we are trying to do a prediction where we actually have a sliding window. So this one is calculating basically the last 3.5 hours, which is 42 measurements, and trying to figure out what will the next 6 measurements be. In this case, it's just adding the last usage 6 times. So there will be 48 measurements. 6 of them will be, or 7 actually, will be the same. And that comes much closer to the line. So what you see here is actually the blue diamonds is a forecast that was made 30 minutes before the dark blue line. The dark blue line is the actual 4-hour rolling average, and the light blue is 30 minutes before it happened, what was predicted. It's still a bit spiky, so we tried to see if we could flatten it a bit. And we did that by taking the last 6 observations rather than only the last observation and putting that into account. So this is again the last 3.5 hours, and then a prediction of the next half hour being the same as the last or the current half hour that just happened. It's a smoother curve, and it seems to be close to the actual MSU for our rolling average. This one actually gives us, it predicts that we cross the line in interval 22, I think it is, and it is actually crossing in 23. The prediction of 22 would come back from around interval 17. So it gives us close to 30 minutes to react. I guess when the prediction was done, it would tell you 25 minutes, but it actually gave you 30 minutes to react. And just for comparison, the actual load was going up and down, as we saw on the first slides. So predicting this from current is hard, as it goes up and down and up and down. But it seems like we have a pretty good curve here.
Yeah, you can say that the advantage of this curve compared to the other ones we looked at is, the very first curve where we're just using the 4-hour rolling average isn't very sensitive to what's going on right now. Whereas if we're just looking at what's going on right now, it's going to be all over the place. 1 minute it's going to say, oh, we're about to go over. Oh, no, I didn't mean that. We're not going over. And this one gives you sort of a little bit the best of both worlds. And the interesting thing here is not only do we predict half an hour in advance that we're going to cross the threshold, but we're consistent from that prediction that the following predictions every 5 minutes continue to tell us that, yes, we reconfirm that we're heading over the threshold.
And one thing for sure here, it's hard to predict, and especially about the future.
Yes. And we're looking at one example here, and obviously there's going to be different usage patterns at different installations, and it's important to try these models out in your world and see which ones actually give the best predictions. But that's the nice thing about having a lot of historical data is you can go out and sort of simulate this on some recent cases where you've had problems with your rolling 4-hour average and see, okay, well, which model would have helped me predict that this was going to happen.
So, yeah. So to enhance the model, would it make sense to go back? This is a picture of almost 3 months, and there's definitely a weekly pattern. Would we be able to apply that weekly pattern to the model to make it even more smooth to the curve, knowing what to expect of the next 5 minutes, maybe?
Yeah, and also potentially even going further back, to look at seasonalities. If your workload is such that you have a very big peak, the days right up to Christmas or Black Friday or something like that, it's nice to know, well, how did this look last year? So, you can use that information together with your real-time analysis to see, are we really in trouble, or is this just going to be the normal Black Friday effect that we're seeing here?
So when you have sort of some confidence that you're going to break your desired max MSUs, whether it's software entitlements, whether it's capping or bad priority, then you need to figure out what to do. So what is the potential actions that you can do to actually eliminate or not eliminate, but mitigate the climbing MSUs? We listed something here. There's probably more, and there's probably something that you would have that would be unique for your installation. You could stop lower priority address spaces. I know some places you would have a service class that are assigned 0, or say MSUs, no guarantee 0, so they will actually stop the work. Could be a batch job running that you want to sort of postpone for an hour or so. You could choose to shut down your sandbox LPARs, reduce test system usage or whatever. You could pause monitoring. DB2 subsystems are, especially the SQL monitoring is quite heavy. And it's a trade-off that you need to decide whether you need your monitoring right now or if the plans or packages are doing the same day in, day out, so you can actually live with the monitoring you have from less peak periods. You could decide to reduce the number of batch initiators to sort of level out the batch, so it's not using that much resources. Thing here is that if you have 10 to 30 minutes to react, you would need to plan this. You would need to have a sort of a guide on which action to take, in what order, and maybe even a estimate of what's it going to save you, how it's going to save your MSUs.
Yeah, and potentially, I think we looked at this peak. It's actually happening at night, so it may just be some operator who's looking at this. And the more you can have things pre-cooked and ready, so it's simple to make the decision. What are the criteria to make the decision to take an action, and simple to act, that they know exactly what buttons to push. The more likely it's going to go well.
Yeah, let's move on.
Good. So some other use cases that are interesting. Zip eligible workload, I'll show you an example of that. Vertical affinity, we also have an example, and some kick stuff. There's some other ones we're not going to go into details about here, but Kix transaction looping, typically you can see that because Kix is using corresponding to a whole processor. Increased DDF workload, number of how much your high importance workload is using as a percentage of your available capacity, WLM statistics like performance index, velocity, things like that. I could see someone wrote in the chat also another use case would be application-wise, looking at it in terms of application or business unit. Since one of the things we work with a lot is trying to tag this technical information with information about what's the application, what's the business unit, what's the business activity that's going on, because it might be very important for you to know that this is our NetBank that's driving this rather than just some internal process. So very good point there. Let's just take a look at zip eligible. Now, zip eligible, as you know, when things are eligible to run on zip and run on zip, you're going to save a lot of money. But if your LPAR is configured in such a way that you have too much zip eligible workload for the number of zip processors available, it's going to spill over and run on a CP. So in the top graph, we see what's running on the zip, and below we see what's running on the CP, but could have run on zip if zip was available. And in the blue LPAR, we see very clearly that it's running up to one zip processor, which is available to this LPAR and just can't get anymore. So it starts spilling over to the CP. And that's going to both certainly have cost implications, potentially also performance implications for you. So what can you do in this particular case? Well, you can stop or delay the work that's causing the problem. You can do some analysis with the SMF30 or something like that to see particular which workloads are causing it. But another simple solution might just be to add some additional zips to this LPAR, just to configure an additional zip online in this particular case. Vertical affinity, as I mentioned before, ZOS is going to go out and assign different vertical affinities to your processors based on the weight of the LPAR and the portion of the total weight. And a low vertical affinity basically means that you're sharing that processor with a lot of other people, and the chances of your cache getting overwritten by someone else is quite high. Whereas with high vertical affinity, you have it's closer tied to your workload, and the chances that you're finding your data in cache are much higher. Things will run much more effectively. That's why high vertical affinity is good. And here we see a case where we're actually running with very low vertical affinity, mostly low and medium. We react to that by adding a little bit more weight to this LPAR, and that causes us it has to recalculate the allocation of the processors, and suddenly we're getting a high processors for a lot of the workload. So this will just run much more efficiently. So definitely something that's worth looking at in near real time.
And you can say if you hit the capping, you actually have the opposite. So if you mirror the graph and say, when you hit capping, the system will actually lower your weights a little bit, and you end up, even though you thought you had a high processor in your LPAR, you don't, because the weight will be lowered like this one.
Yeah, and that's something that's good to look at in near real time. So you're looking at a historical analysis, you're going to see, oh yeah, you know, we're getting high processors most of the time, but exactly in those capping situations, you risk suddenly losing your high processors because of the small adjustments in weight it's going to make to bring down your MSU usage. Kicks response time is another one that's really good to look at in near real time. Here we see, you know, we're just looking at Kicks response time above a threshold of half a second. So in the first interval, we see everything is running half a second. Then we start seeing a few things running over half a second. And then suddenly more and more and more, and even things running in, you know, over 20-second response time. So this is something that's critical to catch, particularly if it's an important online workload that's running. And again, it's a question of going in and identifying the region and the transaction, and looking at the potential look at the LPAR capacity. I mean, is this a kicks problem that's driving this, or is it just your LPAR is so constrained that it doesn't have enough capacity and everything is slowing down? Similarly with add-ins, if you suddenly see a huge increase in the number of add-ins, you know, here we're seeing no add-ins and then suddenly a few, and then in this interval, suddenly 80,000 add-ins. That's definitely a problem you want to be reacting to. Again, you start by trying to identify the region and the transaction that's driving it, and try and fix the cause. A simple thing to do would be simply restarting the failing kicks region in this particular case. Good. I'm just aware of time, and we're at our last slide here, and then we'll have some time for some discussion and question and answers. But I'll let you take this one, Frank.
Yeah. So the challenges and in this is time. So you have a short time. You need to look at your SMF data relatively regularly, probably at short intervals. If you have half an hour intervals, you will not get the next data point maybe until it's too late, right? Our focus is on the small types, as Stephen mentioned. SMF 70, it shouldn't be a big thing to process them, and it's relatively fast. But also you have short time to analysis, so you need to have a plan on that. When we get this alert, what do we look at? When we get information that we are about to break our 4 rolling hours, that we have lots of kicks, add-ins, or whatever alerts you will get, where do we go to actually figure out whether to act on it or to not act on it, and if to act, how can we do, what action should we take? And likewise, there's a short time to action. If you need to call your system admin 3 o'clock in the morning, it may be too late. When he picks up the phone, he doesn't really recognize your name and not sure what time it is or whether he's awake or not. So times runs here. So predefined checklist, predefined action plans, and if possible, let's automate the actions. yeah, I guess that's the message here. You need to prepare for this. When you get the knowledge, you need to be prepared.
Yeah, and so the thing that's behind all this is having a really good setup, having a good solution that's reading the SMF data for you, unpacking it, a really powerful set of analytics tools, the ability to build alerts so that you don't have to be constantly doing the analysis yourself, but you're getting an alert that something is going on here that we need to dig into in more depth, and then have the knowledge of your system to know what action to take. And these are some of the areas that we work with SMT at SMT Data, is processing the SMF data in a fast way, providing strong analytics tools, and providing consulting around this. So, if you have questions or just want to have some dialogue with us about this, you're welcome to contact us. Here's all of our contact details. With that, I'll just open up if there's any questions from anybody in the audience, or any thoughts about other cases where it could be interesting to look at near real-time data. I don't know, Frank, do you have any questions?
No, I'm just wondering, are people able to unmute?
Yeah.
No.
No.
Yeah, and they're also welcome to write something in the chat. But yeah, it'd be great if we could just unmute if anybody has anything they want to say. Good. It doesn't appear there's any questions, but again, if you just want to take an offline discussion with us, we're happy to hear from you. Here's our contact details. Give us a call or drop us an email. With that, our last slide is the session feedback. Please provide the session feedback. There's a little code here down the bottom that you can scan if you want to get into the session feedback system.
I think
So
people can
yeah.
themselves if they want to now, but maybe there aren't any questions. Doesn't look like it. So, well, with that, thank you both very much, Stephen and Frank. Very interesting presentation. We will be back in this stream at let me see the time, 11:15. With Java shared classes and other corners of performance. So with that, thank you all very much for joining and supporting.
Thank you everybody for joining.
Thank you. Bye.
Bye now.